Although we are very happy and satisfied that fair queuing tries to achieve fairness amongst all the competing users, but as we know, in reality, the world is not fair. What we are interested in is who pays more gets to have a better service. For that, the issue of prioritization comes into play. In this module, we shall understand what necessitates the implementation of priority queuing. If priority queuing is to be achieved, how is it implemented? If there are some variants of priority queuing, how do they differ? And can we look at the working and operation of priority queuing in a more descriptive and closed way as well? Again, the reference is by Chuck Samaria, supporting differentiated class services, queuing and scheduling disciplines. The first motivation that comes naturally to our mind is that there are different kinds of traffic sources. Some are real time, some are non real time, some are even interactive. It means that we need to have a relatively simpler queuing and scheduling discipline that is able to entertain a large range of service classes. We need video transmission on the same IP based network. We need voice over IP service. We need interactive command and response implementations. And we also need flexible and elastic effort services. Priority queuing is implemented in a queuing and scheduling discipline by first identifying that there are different priorities, and then each priority flow or traffic is to be given a treatment according to its requirements in a separate queue. So the packets first need to be classified and placed into different priority queues. The packets which are processed at the head of the queue must be adhering to the condition that all the queues of higher priority have already been serviced. Naturally, this has started to look somewhat greedy for the high priority queues, but this is what it is meant to be like. Within each of the priority queue, the packets are serviced simply as first in, first out, because the packets in a single queue can only be treated with the first packet at the head of the queue going first. Visually, we can see that compared to fair queuing, we have lesser number of queues. These queues have been declared as highest priority, middle priority, and lowest priority. It means that the flows have to be classified now according to which priority class they belong to. And then the packets would be inserted in respective queues and would be treated in a first in, first out manner. You can see, if you look at the highest priority queue, the green flow is considered to be the highest priority. But there are two sources, the one shown in yellow and the one shown in orange, which belong to the middle class. And all the other flows belong to the lowest class. It means we actually have many to one mapping in the case of lowest priority, and we have a one-on-one mapping for the highest priority. If you want to determine how much time it takes for an arbitrary packet in a queue, we'd have to look at which priority class this packet belongs to, number one. Number two, if this packet is to be treated, have all the packets belonging to the higher priority class have been treated or have been processed? If these have not been processed, it actually means this packet would have to wait in its respective queue. Mathematically, if we are looking at the departure time of ith packet through kth queue, we can look at the total time it takes. It would be equal to the residence time of the packet in the queue and the service time of the packets before it. So all the packets which belong to the higher priority queue would be accumulating their service time in T sub Si, whereas the residence time of this packet is the time when the packet arrives at the queue and then keeps on waiting for the higher priority queue packets to be processed first. The variants of priority queue can be grouped into strict priority queue and rate controlled priority queue. Strict priority queuing, actually, as the name implies, is rigid. That is, packets in a higher priority queue are always given preference over low priority queues, no matter what happens with the lower order priority queues if these lower order priority queues gets overflown and everything. But in rate controlled priority queuing, the higher priority queues are always given treatment and preference over low priority queues subject to a condition. And the condition is the amount of traffic that the high priority queues are getting have to be below a user configured threshold. It means the network is only going to give high priority queue priority if the high priority queue does not exceed a certain number of packets. If the number of packets in high priority queue consistently are coming in at a very fast rate, the low priority queue packets have to be treated eventually. And that is why it is called rate controlled priority queuing.